Hey everybody, Chad from Patriot Astro. Welcome back, or for the new people, welcome aboard. Today we're going to get into the first of multiple processing videos for processing exoplanetary transits. There'll be multiple videos published on this. The first one today we'll cover is AstroImageJ or AIJ. We'll follow that with a video that covers hops and then finally exotic. But I think it's important we cover AstroImageJ first. You might be asking why, and the reason is pretty simple. I think it's important that you understand the entire process from the start to the end and understand what tools give you the most flexibility to work with different data sets. AIJ definitely isn't the most documented, doesn't have the best UI, and isn't the easiest to use, but it is the most flexible when it comes to going through your data and creating and plotting your data itself. Because of this, I think it's important that we go through it initially before covering the other packages so that you understand what you may be missing in the other packages, even though they may be easier to use. So you can see an example of the interface here. You're going to scroll down the page and you're going to click here to get to the downloads. You'll see there's multiple operating systems available. There's even a help me file. The thing that bothers me the most is that the documentation is a little bit weak. They've even labeled the PDF documentation partial because it sort of just ends at some point about 3/4 of the way through the documentation. So once we've gotten the file and we've downloaded it, all we need to do is extract it to our system. Once you've dropped it into a directory, it's as easy as just double-clicking on AstroImageJ, and you can create your own desktop shortcut if you want. Now, once you first open the application, there are a couple things that I want you to do. The first thing is to adjust the memory that's available to Java for this application. And the second thing will be to update it. So let me show you how that works. So obviously you need to configure this based on your own machine, but give it as much memory as you can. Maybe assign about 2/3 of your available memory to this. From an update perspective, you can just go in and check the updates. You're probably going to download 3.2 and you'll need to update it to 3.4. That's a very easy process. Now, before we go any further in AstroImageJ, I think you need to understand the data you're looking at. Because the NINA plugin took a lot of the initial workload away from us, you probably didn't have to go search to find a transit, which means you didn't have access to some of the data you're going to need at this point. So I'm going to show you one of the online tools you can use to find transits, or to go back and find your previous transit that you imaged so you can get the data points you need to complete the processing. One of my personal favorites to use is the Transit Finder from Swarthmore College. Now, it's pretty simple to go through the filter. Make sure you at least fill out the minimum requirements, the observatory, time zone, the date window. Then you can go ahead and submit it. You may also want to include things like minimum magnitude of the star and even the depth. And the depth will either be in parts per thousand or millimag. It's the same thing. Now, I'm specifically searching in such a way here that I can find data about the transit that I captured, and that was for HAT P32b around star HAT P32. The first column is talking about my twilight hours, my dark hours. Am I going to be able to image this based on my own personal availability? The second column has numerous links available, and we'll probably see these throughout the processing video. One example of that is an annotated image that'll show me where my star lies in a star field, which can be very helpful later on. We'll definitely be back here later. The next column covers both the magnitude of the star in question, as well as the moon's position and potential effect on our transit. This next column here is giving us the time frame of the transit itself, so we can see when the transit starts, when it ends, as well as the hour prior and the hour after. Remember, we need to capture a baseline during the transit to understand what the star normally looks like before the transit occurs. This next column is about the duration of the transit, so it takes about 3 hours and 7 minutes. The next column is time in BJD TDB. This particular time reference uses leap seconds within its calculation, as well as the position of the Earth within the solar system. Here we can see the altitude at each point on the transit timeline. Here we can see a visual representation of the transit like we saw in the NINA plugin. The next couple columns talk about the position in the sky in relation to azimuth and hour angle. And then after that, we see the very familiar coordinate system of RA and DEC. Finally, we can see the period in days. And then the last piece of importance here is the depth in PPT, which is parts per thousand. And right now we're going to go back into ImageJ and open a single file using File Open. Now notice here we have a single frame displayed, and we can see that on the screen in the large area. We also have access to a histogram that's already pre-stretched for us. We have menus and toolbars that are available, much of which we will be using throughout this video. And we even have some image details based on where our mouse pointer is on the image in the screen. Notice we don't have RA and DEC coordinates, and it also says up top, no WCS. This is not solved, and in order to do this properly, we need to solve these images. You can actually do some plate solving within AstroImageJ itself. It does have a hook to the API with astrometry.net, but I can't even imagine trying to run this many images through astrometry.net's API. So instead, what we're going to do is we're going to use a local installation of ASTAP. So we're going to use ASTAP to batch solve. Notice it's already set to WCS. That's the default. We're going to go up to Tools, and we're going to batch solve these files. We're going to go into our light frames. We're going to select all of our light frames, and then we're going to go ahead and it'll start up. So as ASTAP goes through the process, what it's actually going to do here is it's going to clone every file as it solves it. So it'll save the original file as a .bak file, and it'll create a new FITS file with the solved data in the header. When it's done, we're going to grab all our new FITS files, and I'm going to drop them into a solved WCS folder, just so they're all together in one place, and I can leave all my backup files where they pre-existed. Once that's done, we can close ASTAP and go back in to AstroImageJ. Now this time we're going to open up what they call a file sequence. So we're going to go to File, Import, Image Sequence. Make sure you go into your solved files, and you only need to click on one of these. It's going to identify all the other related images in the folder. You can see it found 100 of them. I recommend only having the working light files in a single folder. It'll be easier to work with here. Otherwise, you may have to use some of these filters to specifically identify your light files. One other recommendation I found online is that you should be using virtual stacks. Now, if you have a lot of memory in your system, you may not need to use virtual stacks, but I did have some challenges when not using virtual stacks. There were some performance problems occasionally. So my recommendation is check the box for use virtual stack. Now it's going to go ahead and open up that entire sequence of the 100 images that I found there. Notice we are at 1 of 100. Now these are called slices within the tool. So I'm on slice 1. You can see my file name is here. I have some pixel information about the size of the image, and you can see my WCS and RA and DEC coordinates are in this image. If I use my right and left keyboard arrows, I can go through the slices. So I can start to go through 1, 2, 3, 4, and so forth. There's also a scroll bar below the image that you can use as well. So within AstroImageJ, we can calibrate our files, and to do that, we're going to go up top here and click DP. Now, like most things in AIJ, this can get a little bit overwhelming. The first top line here is about your science files. Those are your light frames. So I'm going to go find my light frames here and identify the folder. This particular pattern doesn't match my files, so notice it says 0 files off to the right. If I know there's a specific pattern within my file names, I can type it here. Now, it's critical to understand that this is case sensitive. Using lowercase HAT didn't work. Even capital HAT doesn't work. Because it's not a full match, I actually need to put an asterisk wildcard there. So I can use capital HAT asterisk, or I like to put asterisks on both sides. It'll always match if it's anywhere within the file name. Notice now that I have a match, it found 100 science files or light frames. Now we can go on to bias subtraction. There's two options here, build and enable. I could just click enable here and then tell it what the file name and location was. Notice here it defaulted to mbias.fits, which doesn't exist. So instead we need to build our master bias. So I'll click build, I'm going to select the directory of my bias files, and I'm going to give it a file pattern that works. In my case, star bias star. Notice it found 5 files. I also want to enable this because I don't just want to build my master bias, but I want to process it against my light frames. Now it's the same thing here for my darks. I could just enable it and select my master dark, but since I don't have one yet, I'm going to have it created as well. I'll click build, I'll give it the directory, and I'll also give it the file pattern it should use, in this case, star dark star. Finally, we'll move on to flats. Same situation here once again. I'm going to build and enable. I'm going to locate my flat files. Now notice that star flat star doesn't work because if I look at my files, it actually has a capital F in the word flat, and this is case sensitive. Now, by default, where do these master files get created? They get created in this science folder, which is your light frames folder. If I don't want it there, I can alter those paths. I can look at Solve WCS, go up one level, and then go up a second level and say, this is my science data folder. This is where I want my masters to be. If that were the case, I could just, like a normal file system, tell it to traverse directories. And in this case, going up 2 directories is .. /.. It doesn't matter to AstroImageJ where it creates the files because it's creating the files and using them simultaneously. So it's completely aware of where it stored the files and knows how to retrieve it. Okay, next we're going to skip over image correction. I'm not going to do any image correction here. So the next thing we need to go to is the FITS header update. So what you need to do is click here to open up the general FITS header information. The section at the top is the FITS header input information it needs. So we need to know the FITS headers in your files that relate to these data points, because everything here at the bottom is going to be generated, calculated, and entered into your FITS files as a result of the processing done by AIJ, but it needs the stuff at the top to be in place for that to happen. So the easiest way that I found to do this is in AIJ to open a single image at this point, and then go up here to edit and then edit FITS header, and that'll show me the FITS header on that file. Now I can use the data there to see how I need to alter the form on the left. So notice my target name keyword is actually object in my FITS header, so I need to modify that. My target, RA, and DEC are different as well, so I need to find that in my FITS header and alter the parameters so AIJ knows where to look in the FITS header to retrieve that information. You need to make sure that all 6 pieces of information at the top here are valid and can be found in your FITS header. One other point I'll make at the bottom here, we want there to be a field for TDB time. So make sure you have that field as BJD TDB. If it says something else, change it to BJD TDB. Okay, so we can close those 2 FITS header windows as well as the single image we opened and come back to calibration. The next thing we need to modify is we need to tell the form where to pull the target coordinates for the source and for our observatory location. One other suggestion here, go off to the right in the conversion tool and go ahead and click update to update the leap second data. I do find this is a little fluky and sometimes the lookup fails, but it is important with TDB time that we have an accurate number of leap seconds calculated as part of our time frame reference. Okay, now we can come back over to the main window, and I'm going to use 16-bit images because I'm using a 16-bit camera. I'm going to set the output directory for these files to be calibrated_AIJ, and I'm going to leave the suffix of out, and I'm going to go ahead and click start. Now, we're going to get a log file that pops open that'll allow us to watch the calibration process. And we're going to start the way we would expect. We're going to go through the bias files and create a master bias. We can see that's dropped in the folder. Then we're going to go through the darks and bias calibrate those and create a master dark. Then we'll go through our flats and process the flats appropriately. Of course, using the master bias and darks against the flats until we generate our master flat as well. At this point, you'll see an image open on the screen as the system goes through all of your light frames and properly calibrates them against your master files that were just generated. I'm obviously going to speed this up because we don't want to watch this process in its entirety. Once it's done, you can just close out of that, leaving the smaller AstroImageJ window open. Then we can go and open a new sequence. And this time we're going to open up our calibrated files. Select one of the files in the new calibrated folder. And again, open it like we did before, making sure Use Virtual Stack is likely checked. It now opens up our calibrated frames. So when we open the new sequence here, let's talk a little bit about the interface. This little circle I'm moving around with my mouse is called an aperture. And based on what's in that aperture, we can see values up top are changing. The value of the pixel I'm centered on, the peak value of the highest pixel within the circle, as well as the int counts, which are the sum of all the pixels in the circle. So what we want to do is actually enable a different pointer that has multiple aperture capabilities. And to do that, we click up here on the toolbar. Now we'll go into the reason for this soon, but there is a reason we need this specific tool. So you notice here again, the value, peak, and int counts as I move around and center on a star. Notice I can scroll in and out pretty easily with my mouse wheel. And also notice that we are looking at slice 1 of 100. I can use my arrows on the keyboard, or we can click around here on the scroll bar. As I click around on the scroll bar, notice that it jumps 10 images at a time. When I go between images 41 and 51, notice the image seems to move a little bit. If I look in the upper left-hand corner, it tells me the direction of X and Y as well as north and east. Notice X and Y changes somewhere between 41 and 51. The application knows how to properly orient these and align them because of the solving that we did earlier. Now, if I step through these one at a time using my arrow keys, notice that between 43 and 44 is where we get the jump. This was our meridian flip that occurred. Now, any movement like this could end up being problematic. So what we're going to do is take a look to see how dramatic this movement is. So I'm just going to zoom in and center on a star. And here I'm on slice 43. If I move to slice 44, we can see there's quite a big jump. Now, this can be an issue as it relates to alignment of our images when we want to go through the stack and take measurements. So the next thing I'm going to do is alignment. And we're going to go up and we're going to go to Process and we're going to do Align Stack and we're going to use WCS headers. Now, make sure when you go in here that we're going all the way through the slices. Make sure it goes from slice 1 to your highest numbered slice, in my case 100. And I'm going to use WCS headers only. So I'll go ahead and click OK and we'll see the process moves forward. We can watch all of the images be opened one at a time and we can see the slices progressing through from 1 to 100. When it's done, it'll tell you it's done. We'll close this image sequence and we'll do File, Open Image Sequence, and we'll open the newly aligned files. So now let's just do a quick validation. I have my aligned files open. I'll just start going through 10 at a time by clicking on the scroll bar. And we can see we're skipping through 10 at a time. Notice as I click through, I'm not seeing the same movement I saw previously, and this looks pretty good. Okay, the next thing you need to do is find a star, and I like to find a star that's the size of my target star or maybe a little bit bigger. Here I'm going to find a larger star in my star field, and I'm just going to left click it. Now when you do this, nothing noticeable will happen. After clicking that star, go up to Analyze and then Plot Seeing Profile. This is the seeing profile based on the star I clicked. On the left-hand side, this is plotting the light level. Now most of the light from the star is close to the center of the star, obviously. It will even include some of the star glow around the edge of the star. The system has determined that from the center to a radius of 18 pixels is the aperture size that should be used. From radius 18 to 32 is sort of a dead zone we don't care about. And then we have an area outside that from 32 to 48, which is where we're going to sample our sky background. So the way this is going to work moving forward is that we have target stars and comparison stars that we need to measure the light levels of throughout our entire sequence. The inner circle is where we expect to see all of the light of the star. So the star itself, including the little bit of star glow outside of that. This is called the aperture. Then we skip a little bit of space. And then we have a second ring that's called the outer annulus. Now that area should not have any stars in it and should really just be background sky. We're going to take a mean value from that outer annulus, and that'll be our background value. Then ultimately what we'll do is we'll subtract that background value, which includes things like sky glow and light pollution, and subtract that from our inner aperture to give us a true value of the star's measurement in flux. If you're happy with the values you see here, you can click Save Aperture, and that will be ported into one of our next steps. Okay, so now we need to select our stars and start taking measurements. And we're going to click this icon up top, which is the Multi-Aperture Measurements tool. When this opens up, make sure you're looking at all of your slices from 1 to 100. Notice that the aperture pixels have automatically pulled into this form. The next thing we want to do in this section is, in this case, we want to tell the system to use RA and DEC to locate the aperture positions between slices. So we're going to start on slice 1 and select our stars, but we want to make sure we're measuring the right stars all the way through, and we're going to use those RA and DEC coordinates all the way through our solved images to make sure it's consistently measuring the right stars. In this next section, uncheck Halt Processing. That's not important for us here. And then everything you can leave here should be set up as default. We're going to go now to Aperture Settings. Now all of this should be fine. Your aperture pixel counts up top will be different than mine because you clicked on a different star in your own image. And there's some other data you need to modify here. specifically related to your camera. So because I used my ASI 2600mm from ZWO, I'm going to go to their website to pull some of this data. Now I shot at 100 gain, so I can go and retrieve these data points. The first data point I need to get back is my electron count based on my gain, so that's 0.2 in my particular case. If you're shooting at unity gain, it'll be 1. The next option is readout noise. The readout noise at 100 gain for me is right around 1.5. Then I need to do my dark current, and that's my electron per pixel per second, or you may see it reported as electron per second per pixel. I shot at -5 degrees Celsius, so I'm going to go ahead and say 0.001. The last two entries here are related to your camera as well. If you can't find this data, don't worry about it. What this really is talking about is when will you be notified by the tool. So because a 16-bit camera has values from 0 to 65,535, as a general rule in my research, unless you have specific data about your camera for these settings, you can usually set them pretty high around the 50,000 range. Just when you thought you were done, we have to click More Settings. Now everything you see at the top here are pieces of information that will be reported or calculated by the system as it processes all of your images. You can leave it all here, but you may find over time there's pieces you just don't care about, and it'll make your data easier to look at if you get rid of some of these data points. So I'm going to get rid of a couple here that I know I don't need and you probably don't need either. There's actually more you could get rid of, but we'll just start here. Also go down here and check the checkbox to tell the system to always default multi-aperture to the first slice in the stack. It's really easy to get off that first slice when you're kind of looking around at your images, and some of the things that are done by this product will start at the current slice, which could be problematic. We always want to look at the entire sequence. Everything else here should be good. We can go back to our main settings and then we'll click OK. Now we're ready to click Place Apertures. Now you'll notice you get a little help menu that pops up on the left, and it's first telling you that you can add your target T1, right? This is your target star, and you need to know where this is in the image, but all you need to do is find it and left click on it. Notice when I'm mousing over it that up top we have a value, a peak, and int count. Remember, the value is the pixel I'm over at the time. The peak is the highest valued pixel within that inner aperture, and the int count is the total value of all of the pixels within that inner aperture. This becomes important because we usually want to find comparison stars that are similar to our star. So if you know the values of your target star, when you mouse around the screen, you can try to find other stars that have similar values. Now notice after clicking our target star, the help menu changed. Up in the help menu, it now says if we left click an additional star, this will be C2, so it'll be our comparison. Your initial target star is T1, and your comparisons are C2, C3, C4, and so on. Now, how do we know we got the right star? Well, one way is to go back to the image provided by the plugin in NINA that will label and show you your target star and potential comparisons. You can also go back to the transit finder and use the data from there, including something like a Simbad lookup. Now this can be much more complicated than it needs to be. Now another tool you can use is something like what's available from AVSO or AAVSO. When you search and find your target star, we'll show you a graphic with the immediate field of stars around your target. It'll identify some potential comparisons and can even show you variable stars that you should exclude. It's important we don't use variable stars as our comparison stars because we want the only variable star that we're looking at to be our target star itself, which is variable in light level because of the transit. So if I look here and I see there's a large star that it's identified, I can go back based on this graphic and find that large star and see if that's going to work as a comparison. Now in this particular case for me, it's not going to be a good comparison. It's not a good comparison because when I mouse over that large star, due to the exposure length that I used, this particular star became saturated, right? It's got a really high value and peak. Because of that, I probably want to stay away from it, and I'll be forced to find other comparison stars. Now, you can use all the tools that are available to you, or you can just kind of give it a shot here. Now remember, this aperture that we're using is very important because not only does it define where we get our data points for the star itself, but it also tells us for that star how to sample the background sky. So stay away from stars like this, with other stars nearby because you may get a bad background reading as a result of a nearby star, which could then diminish the flux level of the comparison. So let's go look around and we'll try to find some stars that will work for us. As I go around and mouse over various stars, I'm looking at the levels in the upper right-hand corner, and as I find some that works, I can left-click and select them. Now, one thing to note is you don't have to click the star perfectly. Even if I click off-center, it will automatically center the aperture because by default, this icon up top is selected, which tells the system to behave that way. So we go around, find some new stars that could be good comparisons that don't have other nearby stars, and I'll select a couple. So now that we have our target and some comparisons ready, we can look at the help section over to the left, and it tells me either to right-click or press enter to proceed. Now I want you to prepare yourself for what's about to happen to the screen. Once the processing begins, a lot of things open. Now I'm going to speed this up pretty dramatically. This can take a little while. The system is going to go through every single image, and on every image it's going to look at every target star and comparison star you identified, and it's going to calculate a lot of data and put it in this measurements table. You can watch the measurements table as the process progresses, as well as potentially the graphic being plotted as well. Once it's done, one of the first places we want to look is here at the multi-plot reference star settings, and notice that I've got some different colored stars. So for my T1, it fell in the yellow category, which is not ideal, but I'm not going to be able to go back and do anything about that at this point because my target star is my target star. There are no alternatives for that one. But notice that my comparisons here, notably 2 and 4, are in the red level. It means the stars recorded very high values for their peak counts. Now that makes these particular stars as comparisons potentially not ideal. So if we just want to look at this, we can go into the measurements table. So the measurements table from left to right is ordered by target and then comparison 2, 3, and 4. So if I scroll all the way to the right, I can get to the comparison 4 star data. Specifically in this case, I'm going to look for peak C4 to find the peak values in every one of these images for that comparison star. You'll notice at some point, I started getting values above 50,000. Remember, I defined a threshold at 50,000 earlier. That's why this was flagged as red. Now to fix this, I'm actually going to have to pick new comparisons. So I'm going to close everything except for the image sequence window and the smaller AIJ window. Now I've got my comparisons still on the screen marked and I can see where those stars are. And what I want to actually do is select new comparisons and sort of start over here. To do that, I'm going to clear my previous comparisons by clicking this icon. And I'm going to select some new comparison stars. To select new comparison stars, I click the multi-aperture button again. Make sure I'm looking at all of my slices and make sure that I do not have using previous apertures clicked. I still want to use RA and DEC, and I'm just going to start over by clicking place apertures. I'll find my target star once again, and I'm going to go find some new comparisons. Now when I right click or press enter, it'll go through and calculate the data. Now in this case, I selected better stars, and you can see that all of my comparisons are falling in the green. I want to talk to you a little bit about how the data is plotted and look at some additional information that was calculated. So let's go through the important pieces of this window. First, we see we have 8 potential data sets, or 8 lines. Next, we can see what is being plotted on each line. There are a lot of options here though, and if you remember this particular window, that's where these options came from. One of the first checkboxes for each line is whether we choose to plot or not plot the line on the graphic. We only have one thing plotted right now. We can also choose the color, symbol, and whether or not the symbols are connected by lines. We can also scale the data as needed and even shift the data being graphed up or down to prevent it from colliding with other data that we're graphing simultaneously. We can also change or modify the legend to identify any of our plotted data, and can change the fit mode so that we can fit our data to other expected models like a typical planetary flux-based light transit curve. What about all the other stuff? We're going to leave that for another day. So let's go back to our full screen and look at this in practice, specifically for our only piece of data plotted, which is our relative flux of our target star T1. So over here, I can uncheck or check the plot of this, and you can see when I uncheck it, it goes away from the graphic, and then it'll come back when I recheck it. You can see I'm plotting relative flux of T1. I have colors and symbols, and I can enable the line feature here to connect the plotted elements. And I can also manipulate what those plotted symbols are. I do have this blemish here that I want to deal with, so I may need to go back into the measurements to take a look at that. And it seems to be about 2/3 to 3/4 of the way through my evening. So I'm going to scroll down, and specifically I want to look at the relative flux of T1 because that's what's plotted. And I can find my lowest data element in that data set is this 0.89 number. And if I scroll over to the left on that particular line, I can see that that is slice 70, which should correlate to my image 70. Now, I'm not totally certain why the relative flux happened to drop at that point, but it may just be an artifact of my night sky. So now that we know it's slice 70, let's go look at slice 70 and see if we see anything. So I'll go back into the image sequence that we had open, and I'm going to go find around 70, and I'll move back and forth through a couple of those images. And it's kind of interesting, maybe the star gets a little smaller. So let's go into the table and look at FWHM for T1. And you can see that it actually started pretty high and then got pretty low. So this is obviously a little unusual. I wouldn't expect my star to get smaller unless my seeing conditions improved or my tracking improved, but it was just a handful of minutes here. So I'm going to take this to be sort of an anomaly in my data. So I'm going to choose to exclude this from my data collection. Now, personally, I don't find a problem with removing data when it's explainable. I can see what happened to my data. Either my guiding got better or my sky got better temporarily, but it's obviously an anomaly from the rest of my data set. So let's see how we can get rid of these particular data points that are causing me a little bit of a problem in my curve. And remember, I'm not advocating getting rid of data you don't like because it's not pretty. I'm telling you that I know I have a problem in my data set based on acquisition, and I'm going to get rid of those particular data points. So I can look at the graphic and I know where 70 is. So if I go back, that's 70, 71, 69, 68, 67. So if I get rid of slices 67 through 71, I'll probably get rid of this anomaly and give me cleaner data to work with. So the easiest way to do this is within AIJ itself. We don't have to delete the images, we can just delete the slices. So I can close it all out again except for my image sequence window. And if I go to the sequence and if I find the highest slice that I want to get rid of, in this case number 71, once I'm on image slice 71, I can go to my main AstroImageJ window and go to Image Stacks Delete Slice. And I'll delete the slices from 71 back through 67. Now I'm going to speed this up a little bit here. Now notice when I go into my image folder, even though I've deleted the image slices, I did not delete the images. I've deleted the slices in the stack that AIJ is working with. Now because I've removed slices, I need to reprocess my data. So I'm going to go ahead and clear my apertures and add new apertures. Now in this particular case, there is another checkbox we can check to save us some time because we know we had good comparison stars. Rather than trying to find comparison stars again, when we come in here, what we can do is click Use Previous 4 Apertures. And this will basically tell my system to reuse the apertures that I just defined. Make sure we've got all of our slices here. In this case, it is not from 1 to 100 anymore because we've removed some slices. That's okay. And we're going to go ahead and let it calculate. Remember to calculate, it's a right click or pressing enter. Now the data looks much better. We've lost that downward spike at the end, and we should have much cleaner data to work with now that we've removed that anomaly. Now let's learn about another part of the interface that was put up on the screen, and that is our multi-plot main. Now this particular window is how we are going to configure the graphing interface itself. So we have options to set our x-axis values, titles, subtitles, legend locations, and various other labels. We can also scale the x and y axis and even change the plot size of the graphic itself. We can also identify the expected transit ingress and egress as well as our meridian flip on the graphic. Previously, I showed you on the other window how we had 8 lines to use for plotting data simultaneously in our graphic. If you want to plot more or less, this is the value you would change in the main window in order to get more or less lines. You can also change the number of detrending variables, but we're not going to do that in this video. Now, there is another thing here I have to point out, is that everything in AIJ is remembered between sessions. So if you get really lost, or maybe you've already used AIJ and your settings and interface look very different than mine, you can actually go up here in the file window and tell it to reset your preferences, and it'll force you to restart AIJ entirely as an application. But there may be times, especially when you're unfamiliar with the tool itself initially, that you get lost to the point where you can't figure your way back out of the hole you've dug for yourself. Okay, so let's change our plot area size. Let's make it a little bit smaller so it fits on this screen with everything else we have in front of us. Now, from a post-production perspective, I'm gonna zoom and crop certain screens here so that we can really focus on only the parts we're working on. Because if I have to keep you at a full screen resolution, you're not gonna know what I'm doing. So notice at the top line, we have relative flux plotted for the target star. What I'm actually gonna do is disable that, and we're gonna plot some other things here just so you can see the power of AIJ and all of the other data it could plot that could help you understand what you're looking at. Let's go plot the altitude of the object. Now you can see I've plotted the altitude of the object. It pulled that data out of its calculations from the FITS headers when it went through processing, and we can see it looks like a typical altitude chart. Now we can validate this by going back and looking at our transit data that I showed you earlier. And if we go back and look at this, we can see here we started at 64 degrees, peaked at 76, and then ended up down at 53. And this does mirror what we expected. We can also choose to plot the air mass. If you're not familiar with the term, air mass is the amount of air you're imaging through. So if I shoot low along the horizon, I'm going through a lot of air until I get out of the atmosphere, which is going to affect my imaging. If I point 90 degrees directly overhead at zenith, I'm going to go through a lot less atmosphere to get to my target. When I plot these simultaneously, you can see they are inversely related. The higher my object is in altitude, the lower the air mass is that I'm shooting through. Now, if I zoom in here, we'll notice we have a gap in our data set. What is that small gap near our peak altitude? That's our meridian flip, right? We lost some data points when the flip occurred because there was a gap in time where we had to process the flip and we were not imaging. Over here to the right, this gap is our bad data that we recently cut out. So let's get the timing of the meridian flip so we can plot it. If you remember earlier when we did alignment, we said that our particular meridian flip happened between slices 43 and 44. That's when we had the jump in our image. So if I go back to our measurements table and find slices 43 and 44, I can look at the BJD TDB time and determine when our flip occurred. What I'm gonna do is grab the decimal portion of that and enter it here in our main window, and then click to enable plotting of that, and now see that our meridian line is plotted on our graphic. So let's go back and let's turn off air mass and altitude, and let's go ahead and turn back on the plotting of relative flux for a target T1 and our first comparison star C2. Now when I enable plotting of my first comparison star C2, I may want to make some modifications. Let's turn on the connecting of dots with lines, and let's also change the color to differentiate it a little bit more from our target star. We'll also go over, and to get these lines from being plotted on top of each other, I'm going to change the scale and the shift. I can change the shift to drop it down a little bit lower in the graphic so it's not sitting on top of my T1 data set. I'm going to shrink the scale, which will smooth out the line in itself, and we can see that it doesn't dip, that it's actually maybe going up a little bit to the right, but it's more or less flat. Once I'm happy with the outcome, I can go ahead and graph C3 and C4 the same ways. And again, I'll adjust those and I'll move them down using the shift and scale capability. So now I've got my target star at the top, and then I've got C2, C3, and C4, and we can see the data looks good. C2, C3, and C4 are all pretty flat and level. They didn't have light dips, but our target star did have a light dip. Now the question is, did it dip when it was supposed to dip based on the transit? So let's go back and get some more data about our transit. The data we care about right now is the BJD TDB time for our transit, and specifically we care about when it started and when it ended, and we care about those TDB decimal portions. We're going to go back to our main window, and we're going to put it in the section for the ingress and egress data. You can see there's a little button here that lets you see how this will be labeled, and it's automatically set up to label this as predicted ingress and predicted egress. Now that I've got these data points entered, I can click the checkboxes to plot them. And you can see they're actually falling right about where I would expect them to fall for our transit. This is a good sign. Now, one thing I don't want you to forget that most people do forget before they go plot a predicted fitting curve is that you need to go to the bottom of the main window and click this copy icon, and it's going to copy your ingress and egress data points down here to the fit region. So now we want to come back to the T1 line and scroll over to the right and look at the fit mode. Now you're going to go all the way to the bottom of the fit mode options and select the one that looks like a flux light level curve. And we're going to get this pop-up window because we didn't have enough windows yet. Now in the upper left-hand corner of this window, there is a place to put the period and days of this particular planet. And we need to go back and get this data from our earlier table. If I go back there, I can see that this particular planet had a period of 2.15 days, so I'll enter that here. And once that's done, we can actually also lock in U1 and U2 with these checkboxes, and you can see we're getting a light line that is a fit model that looks pretty good to our curve. Now to clean this up a little bit more, we're going to go get rid of our residuals from being plotted. We're also going to increase the thickness of that curve that's being graphed to 3 to make it nice and bright. One thing we can validate now based on the curve that was fit is, did our transit duration match? And if you come over here, we can see that we have hours, minutes, and seconds of the actual transit that we've plotted based on our data. And if we go back and look at our earlier reference, we can see that we found it was 3 hours and 10 minutes, and it was predicted to be 3 hours and 7 minutes. And I'd say that's pretty good. Now, one thing you may want to do is clean this up even a little bit more. We can go clean up the legend here. I'm going to turn off the names of all our comparison data in the legend just to get that off the screen. I'll click the X's for that. I also want to relabel the plot data that we have for our curve to just be the name of the planetary object, HAT P32b. So I'll go ahead and label it, turn it off, and then use the right arrow to force that onto the legend. Now I'm going to come back to the full screen here so you can start to see how all the pieces come together as I make a couple more minor changes. Now there is one other line in the legend I want to remove, but it's actually a result of the fit mode. So what we actually need to do is come back here, select the fit mode curve again, and then within that pop-up window, go turn off show in legend. Now it's certainly not a requirement, but I think it cleans the screen up a little bit better. So now we've got a simplified legend, and maybe we can just clean it up a little bit more from a graphical standpoint. So just to clean this up a little bit more, seems like my data might be clipped on the top end of my graphic. So I'm going to change it from being auto-scaled in the Y range, and I'm going to go ahead and manually modify my Y-axis so my data fits a little bit cleaner. I'm also going to change the title and subtitle. And notice you can move these objects around. There's several other things you can change here. Now, as far as exporting an image, from the graphic itself on the right, you can click Save to save an image of that graph on the screen. You can also, in the main window, click File and choose to save as PNG or a number of other formats. Notice also that we have several other options available to us to export data. If you plan on sharing your data and your findings with the scientific community, you actually need to export a lot of this data appropriately so that you can submit it into those databases. I'm not going to do that here in this video. And then finally, in the bottom left-hand corner, if you ever do get lost, know that you can click to restore all default AIJ preferences. That'll get you back to all of the default parameters and interface settings as when you installed it initially. All right, so as you can see, there's a lot of capability in AIJ. There's the ability to plot a lot of extraneous data and to really dive into your data and your graphics any way you want to, based on the data you collected. Here's my sample graphic and another one I created the other day as well from another ExoPlanet transit that I happened to track. All right, well, hopefully you found this useful and helpful. Hopefully you feel like you can go and actually plot your own data within AstroImageJ now, and you feel a little bit more comfortable with the interface itself. You'll be able to create graphics like these two from exoplanets that I've tracked myself, and hopefully this will just be another part of the hobby that you can enjoy from time to time. Be on the lookout for my other videos on exoplanetary processing, specifically with HOPS and Exotic as two other tools I'll look at. Now get your telescope outside, point it at the stars, and start looking for planets. And as always, clear skies.